consider about high density capacitors, which are mostly used for the biasing purposes, for decoupling, etc. in the amplifier design. When you design the amplifier, we use high density capacitors. High density capacitor means more number of capacitors within small area. So how to get more number of capacitors within small area? Instead of using lumped capacitors, use transistors. Simply use transistors. So you can use transistor size can be very small. You know, there is a law called Moore's law. Every year, the number of components within 1 inch or within a unit area increases or becomes twofold. Now it is, I think, 2.5-fold. This Moore's law gets rectified as per the technology. As technology progresses, Moore's law progresses. So how do you increase this number of components? Realizing the components in terms of semiconductors. So semiconductors can be very small, as we have seen in one of the lectures by Professor Sahu last week or last week. There was a distinguished lecture where I discussed about nano components or nano physics, nano semiconductor materials. So how we can realize small components, small transistors, small devices, active devices. Now we are going to use those active devices as the passive devices. We can always use active devices as passive devices. Advantage is passive device. If you take lumped device, the size is large. If you take transistor, the size is small. So you can pack in more number of devices or more number of passive devices, and use them as passive devices. So that gives rise to high density capacitances or high density capacitors. Now in this, what happens is most devices, they will offer highest capacitance per unit area. That is a major advantage. So per unit area, maximum capacitance you will get using MOS. The reason is there are, as you have seen in the equivalent circuit, there are more number of capacitors. Whether you capacitive, what you can say, that is more capacitive junctions, or more number of capacitive junctions, because there are more number of capacitive junctions, like overlaying of gate over drain and source, between drain and source and the substrate, between drain and source and the oxide. So but then between gate and the oxide, between gate and the substrate, between gate and drain, between gate and source. So all those things, all capacitors are mostly in parallel. When they connect in parallel, they increase the capacitance of a MOS. Then you can have n number of MOS per unit area. They are also can be connected in parallel, so you will get highest capacitance per unit area using MOS device. Only thing is, voltage must be high enough to invert the channel. Unless you invert the channel, this MOS device is not going to behave like a capacitor. It will behave like a transistor or switch. To use it as capacitor, only the channel is to be inverted. So use a high voltage to invert the channel and use the MOS device as capacitor. So that part will be taken care of by the DC voltage that we supply in the bias. Key parameters of these high density capacitors or MOS device as capacitors is the capacitance value is between 8 to 8.5 femtofarad per micrometer square for 0.18 micron CMOS technology. If you are using 0.18 micron CMOS technology, this is the raw capacitance value for MOS devices. You is usually high Q you will get, maximized with minimum length. Length is, we already have seen, length is for the gate length, that gives you, and gate length, gate is the divider between source and drain. Now if you minimize the length between the source and drain, the capacitance due to the two sides, source and drain, that will increase as the distance decreases. So maximize the capacitance can be maximized by minimizing the length. These are some of the key parameters. Then if you put the NMOS capacitor, as we have already discussed, NMOS is more preferable compared to PMOS because of speed. So if we put the NMOS capacitor in the N well, you can see the figure here. The right figure shows you the what is the N well, N-type well. So within the N-type well constitutes the substrate, the oxide, into which you are diffusing the N plus gate and N plus drain and N plus source, and above the well is your gate, polygate is above the well. So when we put the NMOS capacitor, mostly the capacitance we get from the N well, that allows operation at lower voltage. So high voltage operation can be neglected, can be avoided by putting NMOS capacitor in the N well. Mostly that we can do. That is shown here in the figure. Look at the figure. The y-axis is the capacitance, whereas the x-axis is the voltage. The capacitance varies between COX and COV. I am sure you know what is the COX and COV. Now, the NMOS is, for when NMOS is in the N well, it is below the VT value, sufficiently below the VT value. So you don't require high voltage. Voltage required is lower. The rate for is lower voltage. Same with low voltage, you get the same capacitance as the COV. The blue value. NMOS on substrate and NMOS on N well. Instead of N well, if you use a substrate, the value will be, you require more voltage to get the same amount of capacitance as compared to the value of voltage required for the capacitance for using the N well. Here, the nonlinearity, if you look at the curve, there is a nonlinear portion. So the nonlinear portion, from it has a lower bound, it has a upper bound. From the lower bound, it goes to the upper bound, both the curves, red curve and the blue curve, both of them approach the upper bound from the lower bound almost in a nonlinear way, which is something like a exponential. It's not exactly exponential, but something like an exponential, right, which is nonlinear. This nonlinearity, which means by changing the voltage, small change in voltage is giving a large change in capacitance. If you look at here, the curve indicates that small change in voltage gives a large change in capacitance. That means by changing the voltage, we can control small changes with voltage, can control the capacitance. Therefore, this can be used, this nonlinearity, that can exploit the voltage controlled oscillator design. So when you use a voltage controlled oscillator design, a voltage controlled oscillator, in the voltage controlled oscillator, as we have discussed, what we require is a capacitor which is controlled by voltage. So it is a LC circuit. The LC circuit capacitance we are changing by voltage. So that capacitance here we are getting from MOS, and we have a very good control over the capacitance. So this can be used in VCO designs as the varactors. The MOS capacitors can be used as varactors for VCO design. And then will come to high Q capacitance. Quality factor should be high, which means capacitance should be very high. How you are going to get capacitance, high capacitance? This figure shows the capacitor realization of capacitance is shown in this figure. You can see there are fingers from the top to bottom. There are a number of fingers from top to bottom, that is from A towards B. Similarly, there are other fingers which are from bottom to top. They are intermingled, or so they are placed in such a manner that between two fingers there is always a gap. So since between two fingers there is a gap, the fingers are metallic fingers. So two metals or two conductors with a gap gives rise to a capacitor. So each gap is giving rise to a capacitor. The smaller the gap, the larger is the capacitance. And all these capacitors are in parallel. Therefore, since they are in parallel, so the capacitance will increase. The small gap will increase the capacitance, and their placement in parallel will also increase the capacitance. So realizing a capacitor in this manner gives you a high Q capacitors, high value of capacitor or high Q capacitor. This type of capacitors are used in the signal path. In the RF circuit, in the signal path that requires high Q capacitors, so there we use this type of capacitor. Accuracy in this is better than 10%. Parasitic capacitance is symmetric. Just look at the figure. From the figure is symmetric. Therefore, the parasitic capacitance is symmetric. It will be typically less than 10% of the capacitance value. This can be extended. That is the 2D picture. You can extend that into 3D. So in the 2D you realize that type of finger capacitors, then stack them one over other. So if you stack them, a stacked lateral flux capacitor is the next one. This was suggested by Aparicio and his group in March 2002. You can see the reference given here. In this example, they realized CT of 1.5 femtofarad per micrometer square for a 0.24 micrometer process of designing the MOS with 7 metals, L minimum and W minimum length and width minimum is equal to 0.24 micrometer. Thickness of the metal was 0.53 micrometer. Then another way of realizing capacitor is using the fractal technology. I hope you understand what is fractal. If you do not know what is fractal, please read what is fractal in the internet. Search for fractals in the internet. These are basically repetition of the same pattern. The advantage of fractal is within a small area. Suppose you are given a length of 10 centimeter. Can you draw a line whose extension is infinity within 10 centimeter? That you can do using the concept of fractal. That is what is fractal. We in fact worked sometimes back on antennas using fractals, the concept of fractals. So this is basically space filling. It has a space filling capability. So you take a given space and fill it. The space will be filled up using the core. Now you know another advantage is its dimension is fractional. The core that you generate using fractal, the dimension is fractional. The dimension that we know up to now is 0D, which is a point. It has a 0 dimension, no extension. It has only existence, but there is no extension. Then 1D, which is a straight line. 2D, which is a plane or curved line. 3D, which is a solid. So 0, 1, 2, 3. These are the 3 dimensions that we know. These are the 4 dimensions that you know. But 1.2D, 2.5D, those dimensions we didn't. Fractals, the curves that you generate using fractals, or the shape that we generate using fractals, their dimensions are 1.5, 1.28, 1.69, 2.53. So these dimensions will be those curves. Maybe someday we'll discuss about that. We can have a seminar on fractal. On that we'll do sometimes some other time. But remember that there is a curve whose dimension is fractional and which has a space filling property. It has 2 major properties. It is self-similar and space filling. So the curve is self-similar and it has space filling. Using that concept, we can design capacitors. If you design the capacitors, so on that, since it is self-similar and space filling, and it, as I told you, 10 centimeters, your length will be infinity. You can go up to infinity. So you are maximizing the perimeter. So perimeter area is maximized in fractal curves. So you can go up to 10 times or 100 times. So in the design, here you can go up to 10 times increase in the unit capacitance by designing it properly. Using photolithography, only the limitation is photolithography. How much increase you can do, or how much between 10 centimeters, or what is the length that you can achieve, largest length that you can achieve, depends on the technology, photolithography technology that you have at your hand. That determines that. So it is limited by photolithography, the length. Is limited by photolithography, otherwise you can go up 200 or 1000 fold increase in the capacitance. Unit capacitance can be increased that way. But with the photolithography available today, it can go up to 10 times. See, this you can see in this paper by Sanhani and his co-workers, which was published in 97. On the reference paper is given here. Look at this paper where they have realized 10-fold increase in the unit capacitance. Now we have discussed resistors. We have discussed capacitors. What is left as the component, passive component, is the inductor. So let us start with inductors. Now in the chip, how do you realize inductance? You know, inductance that you see in the inductors that you see in the lab, or that you have seen in the pictures in your books, these are coils. Coils give you inductances, that we know. Now coil is a 3D thing. It is a 3D entity. When you are designing a chip, or when you are designing an integrated circuit, putting this 3D inductor is impossible, out of question. You cannot put 3D inductors. Chip is planar in nature. So what you do is, let us take a coil, compress it into one plane. So in one plane, it will become a spiral. A coil which is in 3D, that if you compress into one plane, it will become a spiral. So using spirals, we can get inductors. Spirals are good inductors. So these spiral inductors, they create integrated inductors inductors for integrated circuits using spiral shapes on top level metals. This can also require a patterned ground seal. Sometimes they require a patterned ground seal, but mostly you can avoid it. the pattern ground shield. Below this shielding, ground shielding is not always necessary. Sometimes it may require. Key parameters of this is its Q is quality factor is less than 10. Simply using this, you can get up to between 1 to 10 nanohenry inductance you can get, and it has its own self-resonance frequencies, because it is an inductor as well as it is a coil, which means it has a resistance. Since it is a coil, it is a metal or a conductor of finite length, so it will have a resistance. So it is a RL inductor. It can be an RL resonator. So it has a self-resonant frequency. Usually it is implemented in top metal layers. Because of that, it will minimize the series resistance. Once you put it in the top metal layer, it will minimize the series resistance, because it will be connected in parallel to the resistor, because it is in the top. Below that, the other resistances will be there. They are connected in parallel. Therefore, if you connect two resistors in parallel, the net resistance value goes down. Therefore, it will minimize or reduce the series resistance effect. So these are put in top layers to minimize series resistance. Coupling to the substrate is not there, because it is in the top metal layer. It is not in the substrate, so there is no coupling to the substrate unless you want it. You can connect it to the substrate. Then there is coupling, but mutual coupling sort of thing, that is not there. For a detailed discussion, you can look at Mohan and his group, their work. You can verify the inductor parameters L, Q, etc. using acetic. If you want to look at acetic, this is the website, formosa.ecs.berkeley.edu. Berkeley University usually provides its resources free. So look at this website of the Berkeley University. I hope this is now also available. They have not taken it outside out. So look at this. This is a very good website. Then the second type of inductor is bond wire inductor. What is bond wire inductor? This comes because of the bonding of the wire. So you have a IC and you have a circuit, right? That you are going to package them. So look at this package. There is something written as a die. Die is the IC. Assume that is the die, is the IC. The black point within the IC is one of the legs of the IC. That is to be connected to the circuit. One of the paths in the circuit. There are three paths in the circuit which are adjoining pins. So these are the paths of the circuit. So how do you connect them? What we do is we take a wire. One end will be soldered to the adjoining pin. Other end will be soldered to the die. Now because this wire, we are using this wire itself gives some resistance as well as it gives an inductance. This is bonding these two packages, and adjoining pins are bonded by this wire. That is why the inductance caused by this wire is called bond wire inductor. So equivalent of this is shown in the below. Lower figure or the bottom figure shows the equivalence. From the board, then to the chip circuit, between them you have the bond wire, L bond wire or the inductor bond wire. Okay, inductance. Properties is usually this inductance is of the order of 1 nanohenry per millimeter, and you can achieve up to 1 to 5 nanohenry. Inductance value here, it is difficult to control it because it depends on the thickness of the wire, length of the wire, then soldering point, all those things. So chip package alignment, bond wire height, at what temperature you are conducting, all those things will affect it. Q is much higher than this spiral inductor. It is usually more than 40. In spiral inductor it is 10, here it is 40, more than 40. Another inductor is called the integrated transformer. You must have read that transformer in physics. Two coils are coupled. On two coils, when they are coupled, they form a transformer. You have a primary, you have a secondary. Here also you can see that there are two coils. One is blue, other is green. In a plane, you have two coils in plane. One is blue, one is green. They are coupled. When the two green and blue are coupled, they give you a transformer. Use the magnetic coupling between adjoining wires to get the transformer. Key parameters are L or self-inductance for primary and secondary unbundling wires will be there. Then K is the coupling coefficient between the primary and secondary. K is equal to M by root over of L1 into L2. L1 is for the primary, self-inductance for the primary. L2 is the self-inductance for the secondary. M is the mutual coupling between, or the mutual inductance between primary and secondary. You can design this using packages like acetic or any other CAD package. Then this is another example. This is an example basically of high-speed transformer. Here what we are using is, we are using a T-coupled T coil. This consists of a center tap inductor with mutual coupling between each inductor hub. So we have two hubs with mutual coupling between the two hubs. Okay. So equivalent of this is shown here. The circuit is shown on the left. Right side is the realization, physical realization. This is basically used for bandwidth enhancement. If you use a high-speed transformer, the reference is given here. Basically, this was used for broadband and ESD protection, etc. Next. So with that, we come to the end of our discussion on components. Active component, that is MOS, we discussed. Then the passive RF components, that is resistors, capacitors and inductors, that also we discussed. Now we'll finally come to the broadband amplifiers. I am not going to discuss about the design here. Design etc. will not discuss. Just an overview of the broadband amplifier. Then in the next class we will discuss about other issues. Now, when we talk about broadband amplifier, we are talking about broadband amplifier, or we are discussing about broadband amplifier at the RF radio frequency, which is high frequency. So basically our concentration is on high frequency broadband amplifiers. When you consider high frequency broadband amplifier, the first thing that you will typically do in a circuit, that why you require this high frequency broadband amplifier, because in any RF circuit, the first thing that we typically do is to amplify the input signal. So suppose you consider your mobile phone. In the mobile phone, you are receiving some signal. The amount of signal, the power contained in the signal is very small. It is in nanowatt, not in or picowatt there. not in watts. You want it to amplify unless you want, or with the power that you are, or the signal that you are receiving is of low power, are contaminated with noise. Now on the mobile phone you cannot hear this. If you directly convert that or directly demodulate that, you are not going to get any useful signal, you will get only noise. So what you have to do is, after the antenna you have to put an amplifier to amplify the signal. So typically the amplifier is the first unit after the antenna or before the antenna. The main unit is the amplifier. So on the circuit that you see in the top is your connector. Connector can be antenna. Then from the connector there is a line which is connecting to the package. So whatever you have, the circuit that you have in the mobile phone, to that package, it is connected to that, to one of the pins, right? And so this line which is connecting is basically, if you look at the PCB, you will see small lines, very thin lines on the PCB from the antenna to the circuit. These are the controlled impedance PCB traces. Controlled impedance means these lines will have fixed impedances. When you design this, their characteristics impedance is fixed. That is under your control when you design it. On the PCB, the thickness is chosen carefully to realize a required characteristics impedance. Usually it is 50 ohms or 75 ohms or 100 ohms, something like that. So controlled impedance PCB traces, those are called PCB traces, these lines. On the PCB, they are tracing out a path, therefore they are called a PCB trace. So from the connector, we will connect to one of the adjoining pins of the package. If you look at its equivalent circuit, the circuit is Vin is from at the connector. That the connector will have its own source impedance, that is Z1, so that is the driving source impedance is Z1. Then there is a line. If there is a line, means the signal has to cross that path, that line. So it has to cross that path. When it crosses a path, there is a path length involved. Path length is equivalent to a phase delay. So therefore there is a delay. So depending on the length of the trace, there will be delay. So delay is equal to X. But the trace has a characteristics impedance which is Z2. Now this trace is equivalent to a transmission line. So you have a transmission line after the driving source impedance Z1. That transmission line is connected to the chip. In the chip, as we have seen, the bonded wire, because of that you will get the inductance L1. Then because of the pin, you will have between pin and the ground, there will be a capacitance. So for the pin on the chip and pin on the package, there will be two capacitance, one is C1, another is C2. Then on the output will be realized at the load through RL. So there is RL, across RL there will be a voltage VL. This VL is very small. That is what my whole point of discussion is that this VL is small. You are receiving Vin. Vin is small. Then it passes through Z1, which means it is already attenuated at Z1. Then it passes through a characteristics impedance Z0. Again it is attenuated. Then it goes through a pi circuit of LC. So that is also storing some amount of energy. Therefore, ultimately the VL that you get across RL is smaller compared to Vin. Vin is originally small. VL is still smaller, so that is of no use. we have to amplify the VL. So after VL, we will have an amplifier. So after VL, the first circuit is the amplifier circuit. So after the amplifier, you get the output V out, which is the amplifier output. What is the function of the amplifier? It boosts or amplifies the signal level to an acceptable level where we can do the signal processing. Then another important function is it provides reverse isolation, which means whatever is in the output side of the amplifier will not come to the input side. So you are receiving some signal, suppose you are not receiving anything. At that time, like you are playing with your mobile phone, you are doing a calculation. You are using it as a calculator, or you are looking at it for some other thing. And there are many applications you are using. Some applications and you do not want to get connected to internet, or you do not want to send any information. So whatever you are doing, that there also you are playing with some numbers or some electrical signals that should not come to the antenna. This amplifier actually works as a buffer. It separates that. So that will not come towards the antenna. So that V out that you are playing with when you are using it as a calculator, that will not come as VA, or that will not go to the antenna. So it provides a reverse isolation. What are the parameters of this amplifier? Performance parameters are gain of the amplifier, bandwidth of the amplifier, noise generated by the amplifier, linearity of the amplifier. These are all the parameters, key parameters we consider the gain bandwidth product. So we'll come to the gain bandwidth trade-off or gain bandwidth product of the amplifier. Consider a common source amplifier. And so when you consider, usually when you consider a MOS amplifier, you usually consider a common source amplifier. Like if you are considering a BJT amplifier, we consider common emitter amplifier for amplification. Common emitter amplifier is very good in BJT, but common source is the most appropriate one in terms of APT. So we'll consider a common source amplifier example here. The design of a common source amplifier is like this. The source is common to the output. Source is common to the output. Right. So here you can see the circuit. We have V in, V bias. So gate is biased. Then there is RL. Load is given at VDD. Then you are taking V0 across the output, source and drain. C total is between them, these two, and it is grounded. There you are taking the output across the C total and RL. C total is the total capacitance at the output node. Gain, because of DC, the DC gain A is equal to GM into RL. 3 dB bandwidth. You know what is 3 dB bandwidth? When we say 3 dB bandwidth means what? I hope you remember this, but let me clarify this. That I'll clarify in the next figure. When we get the figure, I'll clarify that. 3 dB bandwidth, omega h. This is for bandwidth. Omega h is equal to 1 by RL into C total. That is the 3 dB bandwidth. Gain into bandwidth product is GB. That is a GM by C total. Now how do you get this? Multiply WH with A. DC gain into 3 dB bandwidth, that gives you GB. Multiply DC gain with 3 dB bandwidth, that gives you gain bandwidth product, that is GM by C total. That is constant. Now come to this figure. In the figure, you can see there is a curve which is flat at the top. Then it is flat. So it is decreasing. After that it is decreasing. There is a slope. So it slopes away from the flat portion. Now when it is flat means its gain is constant. On the y-axis A is the gain. Gain is constant. On the x-axis is the frequency. Omega is the angular frequency. So on the x-axis is angular frequency. On y-axis is gain. Gain is constant over a frequency band. So that band of frequency, the gain remains constant. After that, it decreases. When it decreases to half its value. So suppose at the top it is A is equal to 1. Then it starts decreasing. As you increase frequency, it starts decreasing, and A becomes half. For some frequency, A is equal to half. If A is equal to half of its maximum value, the frequency at which it becomes A is equal to half, that frequency point or that point is called the 3 dB point or half power point. It is called 3 dB point or half power point or 0.707. So these three are common. These three mean the same thing. Power is half, or gain is, as you know, power is half. Power is equal to B square I. So depending on that, 1 by root 2, 1 by root 2. B square I by I, if you use this, VI, B square by R is constant if you take R constant. So V square log of V1 square by V2 square, that is gain. Gain is V1 by V2, so log of V1 square by V2 square, that is equal to 2 log of V1 by V2. And now 2, if you take its half value, this will be root 2. So root 2 is 0.707. That value. 1 by root 2, sorry, not root 2. 1 by root 2, 1 by root 2 is 0.707. And if you take its dB, convert it into dB, then that will be 10 into log of 0.707, that is equal to 3. So all three means the same thing. So half power point or 0.707 point or 3 dB point means power has reduced to half from its maximum value. That is what is 3 dB. So the bandwidth is considered as so long as power is more than half, there we assume that it is constant. The power is acceptable. If it goes below half, then we say that power is not acceptable. Usually we do that. Okay. So now you can, I think if you look at this figure, you can make out what it makes. Given the origin pole, GM by C total, higher bandwidth is achieved only at the expense of gain. You can see, because to increase the bandwidth, you have to expand the gain. So if you want to have more bandwidth, you have to have less gain. If you have to have less bandwidth, you will have to have more gain. The origin pole, GM by C total, this is called origin pole. GM by C total, this must be improved for better gain bandwidth product. If you have a better gain bandwidth product, you should have GM by C total should be better. Now, how to improve it? How do you improve the gain bandwidth product? Or how do you improve GM by C total? Well, this will complete our discussion for today. Assume that the amplifier is loaded by an identical amplifier. So if the first amplifier has characteristics A, the second amplifier is also having the same characteristics A. That is what is called identical amplifier. So assume that the amplifier is loaded by an identical amplifier. Now loaded means instead of taking the output or putting the output of the amplifier to a load of R, so RL, replace the RL by another amplifier at the output. Assume that the amplifier is loaded by an identical amplifier and fixed wiring capacitance is negligible. Neglect all the capacitances. because of the ONE. Do that. Then we know GM is equal to mu n COX W by L into VGS minus VT, and C total is proportional to W. Now GM is proportional to W. If you look at this expression, GM is proportional to W, CT is also C total is proportional to W. Therefore, GM by C total, when you compare them, they will be proportional to VGS minus VT by L. Why it is proportional to VGS minus VT by L? What happens to other parts? Now W, since GM is proportional to W, C total is proportional to W, in their ratio there will be any W. Suppose X is proportional to A and Y is proportional to B. Then you can say X is equal to MA, Y is equal to NB, then X is proportional to A, Y is also proportional to A, then X is equal to MA, Y is equal to NB, X by A is equal to MA by YA NB, NA, so A will cancel out M by N, so there won't be A. Similarly here there won't be any W. So GM by C total will be, when their proportionality is considered, it will not contain the term W. Then what about mu n and COX? Mu n is a constant, COX is also constant for the transistor. So then those two are constant, so in the proportionality there is no business of constant. That you take out. What is remaining is VGS minus VT by L. Therefore, GM by C total is proportional to VGS minus VT by L. I hope that this much you understood. How to improve GM by C total? We have found out GM by C total is proportional to VGS minus VT by L. So, to achieve maximum gain bandwidth, that is, we have to improve GM by C total in any given technology, use minimum gate length. L is reduced, GM by C total will increase. So use minimum gate length. Then bias the transistor at maximum. Bias the transistor at maximum means VGS minus VT should be maximum. So bias the transistor at VGS minus VT, maximum VGS minus VT. When the value, now when you are biasing it, when you reach the velocity saturation, then higher VGS minus VT, that will not yield any higher G. So when you are doing this biasing can be done up to a certain point till the velocity reaches the saturation. Beyond that there is no point. It is not going to yield higher GM. So beyond that there is no point. So you can bias it up to the point when it reaches the saturation. Suppose in case of fixed wiring capacitance, large fixed wiring capacitance, we said that we can neglect the fixed wiring capacitance. Now suppose there is the fixed wiring capacitance is large. In that case, you have to consider the power consumption. When it is large, you have to consider the power consumption also. So this is about the gain bandwidth improvement. Now let us conclude. For conclusion, we will consider the constant gain bandwidth is simply the result of single pole roll-off. It is not fundamental. It depends on single pole roll-off that we have seen. It implies a single pole frequency response may not be the best for obtaining gain and bandwidth simultaneously. Single pole roll-off is necessary from short circuit, like for stability, but it is not required for broadband amplifiers. Definitely it is not always necessary for broadband amplifiers. With this, we complete our discussion for what we started today. about the MOS transistor, and then the circuit elements in the MOS transistor, and finally the gain bandwidth product. Now, with these discussions, we have built the foundation for going to amplifiers that we will be discussing. Now, please remember that this